Hi, everybody. This is Dr. Nigro with a chem calculation screencast. This screencast is going to focus on infrared spectroscopy or IR spectroscopy. In an earlier screencast, I talked very generally about what spectroscopy is and what it measures, but we're going to focus in a little bit over the next couple screencasts on the specific techniques that we come into contact with throughout AP chemistry. Now, again, for all of these, we are doing a very surface level look at these techniques. When you get to general chemistry and more importantly, organic chemistry in college, you're going to get a much more thorough overview of what these techniques are. We are looking at them from a very, very far away lens. We're not focusing in very deeply, but it is important that you understand generally what these techniques can do for you, and then just a brief look at what the output is for one of these experiments. All right, so infrared spectroscopy utilizes radiation in the infrared range of the EM spectrum. All right, and so that energy is relatively low in terms of some of the other techniques that we can look at. All right. So, what that energy can do is if you have a molecule, as shown here, and you irradiate it, two things can happen. That energy is absorbed by that molecule and it utilizes it to produce some kinetic energy. It converts that energy into kinetic energy. But it's not enough energy for the bonds to break fully. So instead, they start to stretch. So they move back and forth. So, in other words, the bond gets excited, if you want to think of it that way. Another option is that they can bend. All right. So one is a stretching of the bond and the other is a bending. But the key here is that there is no bond breakage. All right. You do not have enough energy to break those bonds. There's just not enough energy for that to happen. All right. So this technique is a low energy, relatively speaking. I mean, IR can still, yeah, anyway. All right. And you get different bonds requiring different amounts of this energy to move. All right. All right. And that makes sense if you think about it. All right. If you think about a single bond, if you want to stretch a single bond, it's probably not going to take quite as much energy as if you want to stretch a double bond, which probably doesn't take quite as much energy as if you want to stretch a triple bond. All right, so the amount of energy can vary within that IR range, and different bonds will be affected differently. All right, another way to think about it is the way those electrons are shared. All right, it could be that a carbon carbon bond has a very different stretching frequency, stretching wavelength than, say, a carbon hydrogen bond or a carbon oxygen bond. All right, so where this energy is absorbed is going to be important because it's going to give us some information about what types of bonds are present in terms of single, double, triple. It also can give us information about what atoms are involved within those bonds. So that's going to be important as well. All right, now I have a very simple setup right here for an IR experiment. All right, first your light source. All right, that can be any light source. It could be some sort of bulb that has all types of wavelengths, and then the machine focuses only on that IR spectrum. All right, that allows the light to move through your sample. Now, your sample can be any phase in this experiment. So you can have a solid, a liquid, or a gas. That's an R. All right. That energy is then absorbed by the sample, and then what remains goes through the detector. All right, now the detector and the recorder. All right, this experiment measures light that is transmitted. All right, so you see valleys where light was absorbed. All right, we'll see other techniques that show you what was absorbed. So you have peaks where things get absorbed. This just happens to be a transmitted spectrum. All right, so what does that look like in terms of the output? So the IR spectrum looks like this one that I have here. You can see this says transmittance, and this is 100% transmitted. So this is 100% of light got through. And then that is by wave number, which is similar. It's a conversion from wavelength to wave number. It's actually much closer to frequency if we want to get down to it. All right. And you can see that the frequency number is dropping. All right. Now, this would be an example of light that was absorbed because it is not present. We have a big valley right there. So that light did not make it through. So something within the molecule utilized the energy of that light at that frequency to do something within that molecule, whether it is stretching or bending the bonds. All right. So again, these molecules show what light does not get through. All right. What we use this most often for is fingerprinting. So it can provide a fingerprint for the molecule and whoops, ID the presence of bond types. And that can be the order, first, second, or third, and or atoms attached. All right. What it does not do, it doesn't provide detailed structural info. To do that, you need to use in conjunction with another technique. All right. It's it's best for this idea, this fingerprint idea. So let's say you have a molecule of known structure, you determine its IR spectrum, and then you have a sample of unknown structure and you determine its IR spectrum. You can compare those two spectra, and if they match, then you can be pretty confident you have the same molecule. If they do not match, you can be pretty confident that you do not have the same molecule. You can also use certain stretching regions to identify particular components of a molecule. All right, so for example, down here I have two IR spectra. We'll answer these two questions in just a second, but I want to point out this big peak right here. All right, you can see it's down here too. All right, this is the OH stretching region. So this is where if you have an OH bond within your molecule, and you apply energy at this frequency, then that bond will use it to stretch. All right. So whenever you see that big wide peak, you know that there's an OH group within the molecule, but that's all you know. You don't know what it's attached to. You don't know how many of them there are. You just know that there is one present. All right. Similarly, these structures, these two pictures don't show it, but there are other pictures that have a real steep peak right here. All right, and that peak would indicate the presence of a C double bond O, which is known as a carbonyl, all right, component within your molecule. But similarly, it doesn't tell you where they are and it doesn't tell you how many of them there are. You just know that they're there. All right, so IR spectra can be used to compare one to another to rule in or rule out particular molecules. It can also be used to identify pieces of your molecule. There are tables of information that tell you where these stretching and bending bands should be. So you can use those to map out what's present within your molecule based on that IR spectrum. All right, but let's get back to this question. All right. are these two spectra the same or different molecules? So I'm going to call this A, call this B. You can ignore my carbonyl. All right, if I look, all right, I would say different. All right, the spectra are similar, but not identical. All right, in particular, if we look, there's clearly something going on right here that is not present down here. All right, there's also something here that is little, but not quite the same. All right, there's also some differences here and here. All right, there's also some differences here and here. So there are some similarities, but it is clearly not the same molecule. They would have identical IR spectra, and they do not. All right, what about compared to the IR spectrum above? All right, so let's call this C. All right, which of the three molecules is likely to have some structure in common? Okay, so there I would say A and B likely have some structure in common. And I would say because they have oops, some similar bands in their spectra. All right, if we look up at A, or sorry, C, all right, you can see, well, we're missing, right? That huge peak is missing, right? So that's clearly something very different. All right, other than that, there's really not a lot that is similar between C, A, and B. So I would say C is a completely different molecule. It's probably not got a lot in common. All right. Whereas A and B definitely have that OH group is present for both. There's some similarities in the rest of their spectra. They don't look exactly the same, but there's definitely something like this piece is here. So I would say those two molecules probably have some stuff in common in terms of atoms and connectivity, whereas C is a very different molecule. Okay. So again, that's just some examples of what you can do with IR spectra. We are not going to dig into identifying specific stretching and bending modes within these spectra. We are going to use them as a way to fingerprint and compare two spectra. But the key here is what that energy is doing within the molecules. You need to keep in mind that because infrared light is lower energy than some of the other spectroscopic techniques we're going to look at, it is only able to bend and stretch bonds within our molecules. There's no bond breakage happening. There is no electron transitions happening. It is literally just the molecules utilizing that incoming energy, converting it into kinetic energy, and then stretching and bending the bonds within their molecule. Okay. Other than that, IR is of the four that we're going to talk about, probably the least covered on the AP exam outside of its general definition. So if you understand what I'm talking about here, you should be all set. All right. If not, let me know. I have some other resources that you can look at.